Hydraulic system fundamentals. Objectives of this chapter. Bless you. Objectives of this chapter are to describe the basic properties of hydraulic fluid in a hydraulic system. Different systems use different fluids. Some of them are more viscous or thicker than others. The main thing that you have to worry about is the temperature, ambient temperature of the environment that it's operating in. You try and run a bulldozer in northern Canada, it's going to operate completely differently than if you're running it in Miami. Explain the principles of fluid flow, laminar flow, and turbulent flow is the only two. Describe the relationship between resistance and pressure in a hydraulic system. Pressure is defined as resistance to flow, or created by, not defined as, created by the resistance to flow. Describe the different types of accumulators. There's 4, I think. Describe how intensifiers and hydraulic power units are used in a hydraulic system. All an intensifier is looks kind of like a step down cylinder, I guess, for lack of a better word. A large diameter piston on one side and a small diameter piston on the other. Whatever pressure you put in to the large diameter is multiplied to the smaller one, which is kind of cool. List differences between cutaway, pictorial, schematic diagrams. Hydraulic principles are based on the fluid power or fluid flow principle, the properties of liquids which are used in the transmission of energy. Hydraulic fluid is the liquid used in hydraulic systems to transfer energy. That makes sense. What else are you going to use? Pizza? That would get messy real quick, wouldn't it? Pizza sauce, that wouldn't be as bad.
Is the hydraulic oil edible?
It depends.
Early, but all of the modern ones are entirely synthetic and would poison you.
Perfect. I love it.
Not all. That is a basic hydraulic system here. They actually call this an electric motor. I find that interesting. In a hydraulic system, that is what is known as the prime mover.
Prime mover.
Yeah. Why? Because it makes it sound fancy.
Like mechatronics.
Yeah.
Yeah.
So you have the electric motor drives the pump. The pump sucks fluid out of the reservoir. The fill cap there is actually vented so that it can let air in to replace the oil that's pumped out. It goes up through the system, through all the valving and whatnot, actuate the cylinders, motors, whatever it is you have in the system. And then comes back down through the return line into the reservoir and is recirculated. The fluid level on there, about 99 and 9/10% of them also have a thermometer built into them. Just a regular red liquid thermometer like you see hanging on the wall. The fluid that's in the system is designed to work at specific temperatures. So if you have internal leakage, what they call blow-by, you'll see a rapid rise in temperature on your hydraulic unit. And if it gets hot enough, you can actually cook the oil and break it down. It loses its operating properties. You can separate the additives from it. You can do all kinds of bad things to it. Not to mention that the hotter it gets, the thinner it gets, which increases the amount of blow-by through any internal leakage, which makes it hotter. But it makes it get thinner, which increases the blow-by. You can see where it can accelerate and very quickly. Okay. Transmission of energy. Both of these cylinders have got the same surface area on their piston, so any pressure you put on one is exerted on the other. Pressure remains undiminished throughout the system. In utopia. In reality, you have losses due to restrictions in the lines and passing through devices and whatnot, like we learned last week. Fluid flow is a movement of fluid caused by a difference in pressure between 2 points. That's what wind is. For the purposes of fluid dynamics, air is a fluid as well as oil is, and liquid, water, you know, beer, alcohol, anything that can exist in a liquid state. Fluid always flows from high pressure to a low pressure, yes.
There is such thing as liquid oxygen, correct?
Hmm?
How do they make it, or how do they get it into liquid form?
They just chill it.
Chill it?
Pressurized and chilled.
Actually, you have to enclose it so that you can chill it. But whenever you pressurize it up, it gets hotter, not colder. You get the molecules closer together and they start banging into each other more, generates heat. So anyway, fluid flows from high pressure to low pressure areas. Again, that's because of the wind. Fluids flow or follow the path of least resistance. Not exactly. Like electricity, it's going to want to follow the path of least resistance, but it will always take every path it has available to it. Okay. There's your turbulent laminar. You guys ever watch the YouTube videos where they show like water flowing out of a garden hose or whatever, and it looks like it's just
Flow, yeah.
the laminar flow looks like it's just there.
Mm-hmm.
You can't see any movement in it at all. Yeah, that's the laminar. And then anytime you try to change the direction of the fluid, Newton's laws say it's going to try and always go in the same direction it's been going in until it encounters the corner. And then you'll get all kinds of weird goings on in there. If you have a tight bend, you'll get a lot more turbulence and pressure loss as a result than if you have a sweeping elbow. So when possible, sweeping elbow is better because you lose less energy in your system. Does anybody know what the law of conservation of energy is?
Energy cannot be created or destroyed, only change form.
Cannot be created nor destroyed. It can only be changed from one form to another. So when your fluid crashes into the corner, there's a pressure drop. That is a loss of energy. If you can't destroy energy on a changed form. So anybody have a guess on what form it changes into? Rick? Heat. It's one of the many ways you can generate heat in a hydraulic system. Fluid flow paths, and go in series or parallel, just like electricity. Series is configuration where there's only one path. Parallel is a configuration where there are two or more paths for the fluid to flow. Piping, that's just like, okay, it's about viscosity, what the hell. Anyway, the top pipe there has got a thick fluid in it. In this case, it says plastic resin. And then the one on the bottom is a thin fluid, they're calling it water. And the water's coming out of the pipe red, we got problems.
Red.
Viscosity index. Viscosity index is a number that represents how much the viscosity of a fluid changes in respect to a specific change in temperature. The higher the index number, the less change there is in viscosity of the fluid over a given range. And desirable hydraulic fluids are those that have a high number or relatively low SUS change. Flow rate is typically determined by the pump and used to affect the piston speed. You ever heard the term meter out?
Yeah.
If you want to control the rate of a piston, if you measure or meter the fluid going into it, changes in resistance on the load side of it can affect the flow rate anyway. If you meter out the non-pressurized side of the oil is leaving the cylinder, doesn't matter what the resistance is on the piston, you can achieve the same speed if you meter out. Pressure and flow are independent of each other, but for the system movement of a cylinder and a load. Resistance to flow. System starts at 395 psi, or no, 400, I guess. But you got 5 pound line loss. You get down 395, and then another 5 pounds of loss there, 10 pounds going around the corner, which turns into heat. Another line loss of 5 pounds, another line loss of 5 pounds, 10 pounds going around the corner, 25 pounds lost through the device. So by the time you get down here to the piston, you start with 400 pounds and end up at only 335.
Is there a specific amount of distance for every line loss of 5 psi, or is it just kind of sporadic?
It's dependent on the diameter of the pipe.
Okay.
So say it's like a perfectly straight pipe just from point to point, does it lose just 5? Or is it every so often it'll still lose 5?
It's every so far it goes.
Could it ever gain? So like a line gain instead of a line loss? No?
No, but it could.
Yeah.
That's like over unity. So, unfortunately, no. Okay, pressure and resistance relationship. The resistance to fluid flow determines the pressure. Pressure is created by resistance to flow. Resistance to fluid flow in a hydraulic system is determined by 2 variables. Load on the cylinder, internal resistance of the flow into the cylinder or to the cylinder. Pressure control. If system pressure is not controlled, a hydraulic pump will continue to create flow, which can cause pressure to keep rising. That's why you put in a pressure relief valve. That sets your system pressure. Because hydraulic fluids are non-compressible, They just keep building pressure higher and higher and higher and higher until something fails. Okay? We want our system to run at a given pressure, so we set the pressure relief valve at that pressure. And no matter how hard the pump tries, it cannot exceed that. Problem is, the pump is going to continue to produce as much as it can, which is going to force the relief valve open, another source of friction, another way to raise the heat of the system. But that's better than things blowing up. Anyway, if the pressure continues to rise without control, the system will burst at its weakest point. The chain is only as strong as the weakest link. Burst pipe or valve is a safety hazard for personnel and equipment in the immediate operating area. Depending upon how the pipe or device ruptures, it may turn into shrapnel. And if it's got, 5,000–6,000 pounds behind it and it breaks loose all of a sudden, you turn that projectile into one that has lethal force.
Oh, homemade claymore right there.
Yeah. Typically, not always, but typically, the weakest point is going to be joint. So if you have a pipe screwed into a cylinder, or pipe changes into or goes into a manifold and then comes out of the hose for flexibility, that sort of thing, those joints right there are typically where they fail. And then a valve is a device that controls the pressure, direction, and or rate of fluid flow. When we get into the lab, there's all kinds of valves that we have to play with. Our relief valve, the main path for the flow is this way. As pressure builds in this pipe, it's going to force the pop off of the seat, and then the whatever, whatever's too high is going to go back to the tank. Let the system pressure down, turn the pump speed down basically, lower the pressure so that the poppet remains seated and all your fluid goes through here.
On that schematic symbol, can you tell me again what that diagonal arrow means on top of the schematic?
Adjustable.
Adjustable, okay. You've got the spring.
The squiggly line is the squiggly line is the spring.
Mhm. Diagonal arrow is adjustable.
Got your pressure adjusting screw, so that's this. Okay. Spring is that. Line pressure. Return to tank, this is tank symbol.
Okay, awesome.
So that would be that port. What is not shown is there's pressure, or sorry, pilot on there.
Okay,
That is not represented here. It's relying on the pressure in the system to open the poppet. There's an internal drain, but that is not a drain, that is a pilot line.
gotcha.
If it were a drain, it would go from here to the tank line.
And what's the horizontal arrow inside the box?
Direction fluid flow. The fact that it is not in line with this tells you that it is a normally closed valve.
Gotcha.
The jam flow creates maximum resistance, creating a pressure spike. If you have no pressure relief, when you find the weakest point, I can't do that up there, I gotta do it down here. find the weakest point. And that defies the laws of physics. Anybody see a problem with it?
It's going one this way and this way at the same time.
Yeah. Now the guy's hand up first.
I think it has to do with the weakest point is where it's going to bust, right?
Yeah.
But it doesn't,
How does that diagram defy the law of physics?
can pressure go like this?
Well, what do you think?
The gauge is still showing pressure.
There you go. Ken?
The other thing I was gonna point out is that pressure would have been felt throughout the entirety of the pipe, so all barometers would read the same thing before it exploded.
Depends on how long it is.
How long? They are pretty close to each other.
Well, in that picture, yeah, but that's a representation. Maybe hundreds of feet of pipe in there, you don't know. But the fact that we have 200 pounds there and 500 pounds here and 300 pounds over there, over unit pressure went up. I think what they're trying to say is the whole system is going to experience pressure loss. You got 200 pounds coming this way, 300 pounds coming that way, all 500 pounds are going to go out that way. So the system is pressurized to something, probably around 500 pounds, and then when it ruptures. Okay. The burst pipe creates a no resistance condition, which means it's going to come out of there quick, fast, and in a hurry. But you notice it specifically states that there's no pressure relief in the system. That's why you want to make sure you got pressure relief up somewhere. Preferably in the main pressure line, which is here. Pressure supplements. Sometimes hydraulic systems must be supplemented for increased efficiency. Hydraulic system use add-on components to help the system maintain or increase pressure and maintain or increase force. Anybody got a guess on what a pressure supplement should be?
Weight.
Half right.
Weight and an accumulator. What's that?
Accumulator. And Mark mentioned the other one early on in this discussion.
Gas, an accumulator,
No,
an
Good guess.
intensifier.
intensifier. Two ways to do it. Accumulators are typically there if you have a large cylinder that needs to move quickly. It's really, really difficult for your pump to keep up with it. So as the load moves, you're going to get a pressure drop because you're going to get, you can't move enough fluid fast enough to keep maintain that pressure. So you throw an accumulator in there and it makes up the difference. Okay, different kinds of accumulators. You have a cylinder with a spring in it, weighted. So there's your weights. Gas filled. You have a diaphragm type that is also gas filled, and then you have a bladder type, which is also gas filled. So the spring loaded, all it's doing is working against spring pressure. The weighted one is working against the weight of the pressing down on the cylinder. The gas filled, as you pump oil in, you're compressing the gas with the piston, diaphragm, or you're moving the diaphragm, compressing the gas that way, and in this one, you're forcing the bladder into a smaller shape, which increases the pressure. And then those are the schematic symbols. So, most common one that I've seen is gas charge. You also notice that it says that that is dry nitrogen. If you put nitrogen, you charge your accumulator with gas that has not been dried, it can get very funky and can actually deteriorate either the diaphragm or the bladder to the point where it will fail, and then your accumulator doesn't do anything anymore. You also can't get the oil back out of the bladder. You can also, depending upon the pressure in the bladder, inject enough nitrogen into the system to cause vapor lock, or other bad things can happen to your system. So I always want to make sure you use dry nitrogen. Spring-loaded accumulator applies force by means of spring. Spring presses the piston against hydraulic fluid inside cylinder, blah, blah, blah. Weight-loaded, it's a weight that puts the pressure on it. Piston gas charged, gas on one side of the piston, oil on the other. Diaphragm, better. Intensifier, there you go. Okay, there's no connection between the low pressure or the large side and the high pressure low side. But as you are applying pressure here, it's transferred through and it's putting all the force here in this little bitty area there, which causes a dramatic increase in pressure.
What jobs can this thing be used for? Like, where would we need a lot of pressure in a small space?
Well, it's not necessarily large pressure in small space, it's just large pressure. If you were going to use an intensifier to do the lock-in on a toggle press, that way your hydraulic system has to run at, whatever set pressure, typically 5,000 psi.
With this,
But you need, 7,000 pounds or whatever to lock in the press to make sure that the mold stays closed whenever you do the inject. Instead of running the whole system up to 7,000 psi, use an intensifier, and that gives you the pressure boost that you need. Does that make sense?
it does a little bit.
So, schematic cylinder, or schematic symbol rather, is a kind of a step down cylinder. What do you think? Thing you gotta remember is there's no oil in here. It's purely a mechanical connection. That is a basic HPU and its schematic diagram. mover, or the pump itself. Did we talk about that in here, or was that the other class? Mechanical power. If the triangle there is filled in like this one is, it tells you it's hydraulic. If it's not filled in, it tells you it's pneumatic. Okay. Also tells you that the fluid is only going to flow in that direction, because that's the way the arrow is pointing. If you had an arrow pointing in both directions, it would be bidirectional. Okay. If it is bidirectional, it's not going to be a pump, it's going to be a motor, which is just, reversible motor. Anyway, you got the tank, which is there. Got your filter, which is on the suction line you can't see in the picture. Suction line, that is that guy. Pressure line goes there. Pressure gauge is there. See, the symbols look something like what the actual devices are. There's not that big of a stretch. And then your pressure relief valve is right there. Okay. System diagrams. Fluid power systems can be illustrated using a diagram. Common fluid power diagrams: pictorial, cutaway, and schematic. That's pictorial. That's schematic. Cutaway is the one where they cut away part of the doodads. You can see what's inside. That'd be pictorial. That is probably not even remotely what the actual system looks like. Your pressure relief valve is not going to be 4 feet in the air like that. Anybody know what a check valve is?
What's that?
A check valve?
It's all one way, isn't it?
Ben's right. One-way valve allows fluid to flow through in one direction, not the other. Cutaway diagram, you can see internals or whatever. Color code for flow of pressure there. Red is the highest operating pressure or system pressure, as that is directly off of the pump before you get to the pressure relief. That is the highest pressure that the system will ever see. Okay. Directly off the output of the pump. Yellow, controlled flow, which that is the bleed off from, no, that's not bleed off. That would be your bleed. So that's your meter right there. That's the internal. Yeah, that's the internal that the other didn't have. Orange is intermediate. Typically discharge from a cylinder that has to go through another valve somewhere. Green is intake or return, zero pressure basically. This you will actually, if you were to put a gauge on it, would have vacuum on it. It's what they call suction pressure. Actually, negative pressure is below zero gauge or below 14.7 atmosphere.
So I'm just thinking out loud, sorry.
Blue, exhaust or return, so anything goes back to the tank. And then white is inactive, which the only place you see inactive fluid is here. And that's not actually fluid in there. The tank is actually slanted on the bottom like that, because that's your clean out port. So you empty out the tank, you open up the little plug there, let the oil out of it, and then you take the tank, the cover off. So you reach up in there and wipe out all the sludge and the gunk and whatever's in there.
So Rod, I have a question, just to help me understand this, in the way I think I understand this. If this were an electrical diagram, this would be wired in series. And that's why we're kind of losing pressure throughout. And for it to be wired in parallel, we would need another motor at the reservoir, basically another source line.
You would need another motor.
Okay, but another line from source.
Yeah.
Would be in series.
You'd have two parallel. You have two lines coming out here.
Gotcha. Do we hook up hydraulic in parallel often? Okay.
Well, not directly off the pump.
Okay.
It would typically go into some kind of a manifold, which would then
Gotcha.
redirect fluid flow to, wherever it needed to go.
I know it's not electrical, but that's where I have more experience, so I'm trying to tie it in where it makes sense.
Yeah. There is, of course, some pressure loss through valves and devices and whatnot. By the time you get back to your neutral line, blue or the green, you essentially used up all your
Amperage.
your juice, and so zero EMF, or in this case, 0 PSI.
Gotcha.
That is the schematic symbol for that circuit. Okay. Reservoir, prime mover, they actually call it a prime mover there. Pump, relief valve comes right off the pump. This is your directional control valve, or DCV. We're going to talk a lot more about these later in the semester, but that is what is known as a 4-3. The 4 tells you how many ports are on it. And the 3 tells you how many different positions it can be in, so here, here, or here. That is drawn as an APB center, so that center position, all ports are blocked. That's what the T in it means, block port. Spring return to center. You got spring on both sides. Manually actuated, so it's got a hand lever on it. And when you push the handle this way, it's going to force this pull that way, so these connections get made here. Okay. So from the pump through to your flow control, and then back to the tank, and then whenever you pull it the other way, they cross. That's flow control. That's actually metering in, which is the wrong way to do it. You tell it's metering in because when the fluid comes from the pump, it can either go that way or that way. That is a check valve. So when pressure is higher on this side, the check valve is going to close. It's going to force it through the orifice. It is an adjustable orifice because it's got the arrow on it. And then into the cylinder, and then it's going to return from there. Going back the other way, because fluid is extremely lazy, when trying to go back this way, when you're retracting the cylinder, it's going to hit the orifice, but it's also going to pressurize this side of the check valve, open it up. So most of the fluid is going to go through the check valve, and very little is going to go through the orifice.
So it's not actually regulating the cylinder.
Yeah, well, technically it is, but incorrectly. That should actually be in this thing, plane. And it should be flipped over.
Gotcha.
So you can retract at full speed, but you meter as it's going up. So put your pressure here, it's going to be pushing on whatever load it's connected to. You can have one on both and hand out if you need to control flow in both directions. That takes us to the review and the activities, which are separate and on canvas.